In mathematics, a matrix is a fundamental concept in linear algebra. A matrix is a rectangular array of numbers arranged in rows and columns. It is typically represented by a capital letter like A, with elements denoted as a sub-ij, where I is the row index and j is the column index. Let me show you what this looks like visually. Here is a 3 by 3 matrix with example numbers. The first subscript indicates the row number, and the second indicates the column number. In general, an m by n matrix has m rows and n columns. Here's what the general form looks like. Matrices come in various types based on their structure and properties. Let's explore the most important classifications. First, a row matrix. As the name suggests, this is a matrix with just one row. It's essentially a horizontal array of numbers. Row matrices are often used to represent vectors in row form. Next, the column matrix. This is the vertical counterpart of the row matrix. It consists of just one column. Column matrices represent vectors in column form, which is more common in linear algebra. A square matrix has equal number of rows and columns. The diagonal from top left to bottom right is called the main diagonal. Square matrices are particularly important as they can represent linear transformations. The zero matrix, also called null matrix, contains all zeros. It acts like the number 0 in matrix operations. When added to any matrix of same size, it leaves the matrix unchanged. A diagonal matrix has non-zero elements only on its main diagonal. All other elements are 0. Diagonal matrices are easy to work with computationally. The identity matrix is a special diagonal matrix where all diagonal elements are 1. It acts like the number 1 in matrix multiplication. Multiplying any matrix by the identity matrix leaves it unchanged. A symmetric matrix equals its own transpose. This means elements are mirrored across the main diagonal. Symmetric matrices appear frequently in physics and engineering applications. A skew-symmetric matrix equals the negative of its transpose. All diagonal elements must be 0. And off-diagonal elements are negatives of their mirrored counterparts. These matrices appear in angular velocity calculations. Finally, triangular matrices have non-zero elements only above or below the diagonal. Upper triangular matrices have zeros below the diagonal, while lower triangular have zeros above. These matrices are useful in solving systems of linear equations. Matrices are like boxes of numbers that can do special tricks together. Let's learn how they add, subtract, multiply and more. Adding matrices is like adding two piles of cookies. You take one cookie from the first pile and one from the second pile at the same position, and put them together in a new pile. Subtracting matrices is like eating cookies from a pile. You start with the first pile. Then take away cookies from the second pile at each position. Multiplying a matrix by a number is like making copies of your cookie piles. If you multiply by 2, you get double the cookies in every position. Matrix multiplication is like a special dance between rows and columns. To multiply two matrices, we take a row from the first matrix and a column from the second matrix. Then do a special multiplication and addition with them. The transpose is like doing a flip dance with the matrix. We turn rows into columns and columns into rows. It's like looking at the matrix in a mirror placed at its diagonal. Great job learning about matrix operations. Remember, matrices are like special number boxes that follow specific rules when playing together. With practice, you'll become a matrix master. Matrices have special secrets hidden inside them. Let's discover how determinants and inverses reveal these secrets. The determinant is like a detective that investigates a matrix. For a 2 by 2 matrix, it calculates add minus BC. When the determinant is 0, it's like the matrix has collapsed into a line. This means the matrix can't be inverted. Just like you can't unflatten a pancake. The inverse matrix is like an undo button. When you multiply a matrix by its inverse, you get back the identity matrix. Just like when you undo an action. For larger matrices, we need helpers called cofactors. Each cofactor is like a mini determinant of a smaller matrix. The adjoint is just the transpose of all these cofactors. The rank tells us how strong a matrix is, how many independent directions it has. A matrix with rank 1 is like a flat line, while rank 3 is like full 3D space. Now you know the secrets of determinants and inverses. These concepts help us understand how matrices transform space and whether we can undo those transformations. Keep exploring the wonderful world of matrices. Let's dive deeper into the fascinating world of matrices. We'll explore powerful techniques like factorizations, methods for solving systems, and other advanced ideas. Matrix factorizations break down complex matrices into simpler, structured components. Think of it like finding the prime factors of a number. But for matrices, Lu decomposition factors a matrix A into a lower triangular matrix L and an upper triangular matrix U. L has ones on its diagonal and zeros above, while U has zeros below its diagonal. This is very useful for solving linear systems efficiently. Q are decomposition factors A into an orthogonal matrix Q and an upper triangular matrix R. Orthogonal means Q transpose times Q equals the identity matrix. This method is crucial in algorithms like finding eigenvalues and in least squares problems. Cholesky decomposition is special. It only works for matrices that are symmetric and positive definite. It factors A into L times its own transpose, L transpose, where L is lower triangular. It's very efficient, often twice as fast as LU decomposition for systems where it applies. Singular value decomposition, or SVD, is incredibly powerful in general. It works for any matrix, square or rectangular. It decomposes A into U times sigma times V transpose. U and V are orthogonal matrices, and sigma is a diagonal matrix containing the singular values of A. SVD has wide applications in data analysis, compression, and understanding matrix properties. Matrices are fundamental for solving systems of linear equations, like finding where lines or planes intersect. Let's look at common methods. Consider this system of equations and its augmented matrix representation. First, we identify the pivot element in the first column. We eliminate the term below the pivot using this row operation. Next, we scale the second row to make the pivot equal to 1. Finally, we back substitute to find the solution. Cramer's rule provides an explicit formula for the solution using determinants. It only works for square systems where the determinant of A is non-zero. To find the variable x_i, you calculate the determinant of a modified matrix A_i, where the ith column is replaced by the vector B, and divide by the determinant of the original matrix A. While elegant, it's often computationally expensive for large systems. If the matrix A is square and invertible, meaning its determinant is not zero, we can find its inverse, denoted A superscript minus1. The solution to the system A times x equals B is then simply given by x equals A inverse times B. Finding the inverse can be computationally intensive, but once you have it, solving for different B vectors is fast. Finally, let's touch on a couple more advanced topics that build upon these ideas. Just like vector norms measure vector length, matrix norms measure the size of a matrix. The Frobenius norm is like the Euclidean length, calculated from all elements. Operator norms, like the 2 norm, measure the maximum, stretching, effect the matrix has on vectors. The 2 norm is equal to the largest singular value of the matrix. We mentioned SVD earlier. Its decomposition into orthogonal and diagonal matrices makes it extremely useful in many fields. It's the foundation for principal component analysis, PCA, used to reduce data dimensions while keeping important information. It can be used for image compression by discarding smaller singular values. Other applications include noise reduction, building recommender systems, and even defining inverses for non-square matrices. From breaking matrices down into simpler parts using factorizations, to solving complex systems of equations, and measuring their size with norms, these advanced concepts provide powerful tools for science, engineering, data analysis, and much more. Keep exploring. Matrices are the Swiss Army knives of mathematics. They appear everywhere from computer graphics to quantum physics. In computer graphics, matrices transform 3D objects, rotating, scaling, and moving them to create video games and animations. In machine learning, datasets are stored as matrices where rows represent examples and columns represent features. Quantum states are represented as vectors, and quantum operations are described by matrices acting on these states. Social networks and transportation systems are modeled using adjacency matrices where entries represent connections. In robotics, transformation matrices calculate arm movements and object positions in 3D space. From pixels to robot arms, matrices provide the fundamental language for describing structured data and transformations in our universe. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.